Thank you very much. So I'm going to take you on a whirlwind tour down to Antarctica and see a few of the sites there, and also look at the subjects of climate change and the Antarctic ozone hole. And you might wonder, does climate change matter to astronomers? The answer is very much yes, because with more water vapor in the atmosphere, because it's warmer, there's more clouds. So there's a very direct link between astronomy and climate change. And I've entitled this The Voyages of a CUAS tie. I'm wearing the CUAS tie of the original design, which went down to Antarctica several times. And then there's a more modern one to celebrate 50 years of CUAS, which has also been to the Antarctic. So that's why Voyages of a CUAS tie. So when I was a student, it used to get cold during the winter. And you had this strange stuff called snow, which provided a pretty backdrop. It also meant temperatures got very low. And I think the coldest meteor watch I did was about -12, which was interesting. It also gave the opportunity for a few visitors to do a bit of observing. And the observing team definitely had quite a lot of fun making various sorts of snowmen. We also had trips away from Cambridge. So you might recognize the person on the left there, who is Simon Menther. And this was a trip to Greenwich Observatory. And we also had a trip to Stonehenge. So I read natural sciences. And after I graduated, I did a one-year teacher training course and then joined the British Antarctic Survey, which is based out on the Madingley Road beyond the observatories. And that got me eventually quite a few trips down to the Antarctic itself. This is subantarctic. This is the island of South Georgia with really quite pretty mountains upon it. The routes down to the Antarctic are quite varied. Most of my trips involved flying most of the way, whether it was to the Falkland Islands, the tip of South America, or to South Africa. And thereafter, either another flight or taking the ship to get to Antarctica. My last trip was to Cape Town as a starting point. So we saw some of the round the world yachts in the harbour. We were taken on a safari to see some wildlife while they moved us out of our hotel to another one without telling us. And then it was the poshest plane I've ever been in, where the worst seating was business class. And that took us to a blue ice runway in Antarctica. And there we transferred to another plane that was perhaps the worst one that I've ever flown on, which was a pre-World War II Dakota with 3 engines to it, unpressurized. We've unheated as well. We flew at 10,000 feet. And all you could do was just sit in your seat and breathe. The reason for my last trip down was that the Halley station had been moved because of an impending crevasse, and they needed a meteorological observer on the station. And as I used to do all the meteorological training, I was an ideal person to actually do the job for real for once. And so that was really quite an enjoyable stay, and you'll see a little bit more of that later. So the bit of the Antarctic that I was mostly involved in is the British Antarctic Territory, a pie-shaped slice of Antarctica running from 60 south to the pole and encompassing most of the Antarctic Peninsula. That area is actually also claimed in part by Chile and Argentina, but under the terms of the Antarctic Treaty, those claims are held in abeyance. And we have currently 2 main stations, Halley and Rothera, some other smaller ones, and a few scattered automatic weather stations. So a typical start of my voyages would be flying into the Falkland Islands on an RAF transport, and then the sites of Stanley itself. And as the sun got low in the sky, if you're lucky, you might see a sun pillar caused by ice crystals refracting the sunlight in the atmosphere. On one trip, I was incredibly lucky in that I saw noctilucent clouds. They do occur in both hemispheres. We're familiar with them here in the UK, but they are very, very rarely seen in the Southern Hemisphere, simply because there's very little land in the right latitude zone. So a few years ago, there was quite a good display of the clouds here from Cambridge. And this is looking across Midsummer Common to the river. And you can see these bluish, violet bluish colored clouds that are still glowing from reflected sunlight long after the sun has set. And these are clouds at the mesopause, around about 80 kilometers up. So really high altitude clouds. And talking of clouds brings me on to the weather. And that was one of the things that I was down in Antarctica to actually observe. It does get pretty cold there. This was one of our ice chemists, and her laboratory was about 1 kilometer from the main station. So she had to walk across. And if it was a bit foggy, then your eyelashes and eyelids do rime up. But as soon as you get into the warmth again, that all melts. Now, people reckoned that going down to the Antarctic is a pretty daunting experience, but I mostly went down there in the summer months, and the temperatures in the Antarctic summer are not vastly different from the Cambridge winter. Particularly at South Georgia, temperatures 4 or 5 degrees Celsius typically, rather just above freezing. Halley typically -5, which is actually quite pleasant because it means that all the snow stays frozen, and walking around in slushy snow is not particularly nice. However, Halley is inside the Antarctic Circle. It has 3 months or so when the sun never rises in the winter. Equally, it never sets in the summer, which can be quite disorientating. But under those dark skies, average temperatures reach about -30, which is a bit colder than in a typical deep freeze, and it can get down below -50. And under those cold temperatures, if you throw a flask of boiling water into the air, it turns to ice almost instantaneously, and you get this sort of explosion of ice crystals. But our stations are at the coast. If you go inland, the altitude rapidly rises, and at the Russian Vostok station, which is getting on for 3,000 meters above sea level, they've recorded the lowest temperature anywhere on the surface of the Earth of -89.2 Celsius. And the Russians used to have these effectively spacesuits to go outside, which warmed the air up before they could breathe it, because a breath full of -89 Celsius air would just freeze your lungs. Looking down from above, this is a mosaic of weather satellite imagery. The Antarctic effectively doubles its size during the winter. You can see, the mouse isn't transforming itself. That's a shame. Whoops, didn't want it to do that. Go back. No, never mind. The mouse is being objectionable. So you can see on the screen there, that sort of grayish area surrounding Antarctica. That's the pack ice that forms during the Antarctic winter and effectively doubles the size. Antarctica, the continent itself, you can see in the middle, is largely cloud-free, and that's because the depressions can't penetrate very far inland. And if we look at this evening's forecast for Antarctica, this is what it's like now. You can see that there are a number of depressions circling Antarctica, but the center of the continent itself is a high pressure area, so very few clouds. And in fact, the bulk of Antarctica is effectively a desert because so little precipitation occurs. But getting there by sea can be something of an ordeal, because you have to cross that stretch of water between the tip of South America and the Antarctic Peninsula, where the furious 50s blow, and the waves can get pretty bad. Indeed, there's been times when you've set sail and some people immediately take to their bunks because even a slight swell makes them seasick, and the sort of weather where the waves are breaking over the bows, they won't be seen at all. But eventually you get down to the more sheltered waters of the peninsula, and there you sometimes get mirror-like calms where the mountains of the peninsula are reflected in the seawater. And along here, we start seeing a few more meteorological phenomena. This is a fog bow created in exactly the same way as a rainbow, but the water droplets are so small that you don't get the separation of the colors. So it appears just as a pale bow in the sky. And I was fortunate enough to see one of these from just outside Cambridge last month. We had a nice foggy morning, and I was traveling up onto the Gogs and looking across, there was this fog bow. We do occasionally get rainbows. These are fairly rare, probably only seen along the Antarctic Peninsula, where it is warm enough for rain to actually fall. And then from the air, we might see the phenomena of the glory, where you get a coloured halo surrounding the shadow of, in this case, your aircraft or your own head. Another interference type thing is this display. This is equivalent to the 22-degree halo that you can see around the sun on a slightly hazy day in this country. But here it's being created by reflection and refraction of ice crystals on the surface of the snow, which is quite an unusual circumstance. But you can see very clearly in this that that central part is much darker than the outside, because the light that should be coming from that evenly illuminated field is being reflected to make the actual halo itself. Off South Georgia, we quite often get these stack of plate clouds, and these may be the origins of unidentified flying objects, because they quite often form when wind is blowing across a mountain range. The wind is then forced to rise. As it rises, it cools and layers of cloud can form. And if the wind is transverse a little bit to the mountain range, the vector winds will proportionally go much faster. And that's why some of these fighter pilots thought they could chase the clouds along the mountain range. But it is just clouds, even though they do look very much like the traditional pictures of UFOs. Another phenomenon of the Antarctic is miraging. And here, these are just distant ice flows rising perhaps a meter or so above the sea surface, but the air near the surface of the ground is acting like a lens. I suppose you could use as an analogy the gravitational lensing that allows us to see distant galaxy clusters and the like when it's bent and focused. Well, it's the same sort of thing, but it's not gravity that's doing the focus. It's the atmosphere that's doing it here. And on the right-hand side there, if you've got a good imagination, you might see the towers of a castle rising into the air. And this is called the Fata Morgana, after Morgana Le Fay, the Arthurian enchantress, who could supposedly conjure castles out of the air. All she was doing was pointing to a mirage in the distance. As the sun gets lower in the sky, the shadows get ever longer. And when that final fragment of the sun drops below the horizon, you might be lucky enough to see either the green flash, or with my eyes, I see it more frequently as a blue flash. And on my last flight out of Antarctica, I could see that the conditions looked to be fairly good for seeing this. So as quickly as I could, I got to a window looking across towards the sun, and I was rewarded with a beautiful steely blue, to my eyes, flash of light as the sun finally set. If you go to the South Pole, though, the sun takes much longer to set, and they've been able to observe the green flash for 24 hours continuously as the sun finally sank below the horizon. Looking the other way, we might see another phenomena. And in Antarctica, the atmosphere is very, very clear. And that band of grey that you can see in the center of the picture, that is the Earth's shadow beginning to rise up into the atmosphere rather than a layer of pollution. Indeed, the mountains that you can see right at the bottom of that fiord are actually 100 kilometers away, which gives you some idea of the clarity of the atmosphere. And obviously, that shadow, if the moon is exactly orientated in the right position, will intersect the moon, and then you get a lunar eclipse. Once it gets truly dark, which for my stays at Halley, it never did, but on South Georgia, I was rewarded with some really truly dark skies. You can see the Milky Way arching right overhead with the Southern Cross there in the center and the two Magellanic clouds easily visible to the naked eye. Right at the top of the image, which I didn't actually see at the time, that's either a satellite trail or a meteor that flashed across the sky. And we get to see in full some of the constellations that you can't see from this country. So here's Scorpius in its entirety with that stinger bending around, ready to hit somebody. I've seen a few comets from Antarctica. None of the ones that I've seen have been terribly spectacular. But in 2006, we got a view of Comet McNaught from Cambridge prior to perihelion. And I observed that from just by the Cavendish, looking across from the Coton footpath. And it had a splendid little tail. But that developed even further once it had rounded the sun and was in the southern hemisphere. I was in the southern hemisphere in 2011 when Comet Lovejoy graced the skies, but sadly I was too far south. I'd got into the land of 24 hours daylight, and the comet wasn't quite bright enough to be a daylight object, so I missed that particular one. At Rotherham Station, you get to see a few oddities. So here's Orion doing a handstand rather than in its normal orientation. And you can also see that to an extent we do suffer from limited local light pollution, because that orange glow on the ice cliffs is actually some of the base lighting illuminating them. But you didn't have to go very far to get to a truly dark site, because we do run a number of optical experiments at the station. Life on a station can be quite entertaining. This is another view of what was Faraday Station, named after the famous British physicist. It's now named Vernadsky, after, at least in Ukraine, a very famous physicist, but he's not quite so well known in this country. And on a small station like that, you can have little holidays when you've got a bit of spare time. One of our visits, we did sail in a small outboard dinghy over into the center of that channel. On a station, life is quite comfortable. When I was at Bird Island, there were 8 of us. We had to do all our own cooking. There was no chef or anything like that. But we managed to rustle up some pretty good meals that on a Saturday night, which was the night you dressed up fairly poshly, did rival some of the meals that you might get in a restaurant here. And for leisure, you could go skiing. I did a mix of cross-country and downhill type skiing. But you had to make quite sure that you put on sunblock, particularly on the back of your legs, because that was exposed to the light from the sun. And the other fun thing to do was skijoring, where you're towed behind a skidoo at sometimes quite high speeds. I think the fastest I got up to was about 60 kilometers an hour, and the skidoo wouldn't go any faster, and I didn't want to go any faster either. So that was just as well. But I learned to ski when I was at school in Switzerland, so I was moderately competent at any rate. Rather, another thing we can do is go climbing down a crevasse. We have alpine guides on the station who are very skilled in mountaineering, and they will rope you up and make sure that you have all the correct gear on. And then you can descend down into one of these crevasses and see the color of the light change from the top, where the ice and everything looks white, and the deeper you go down, the bluer it gets, and finally it's sort of more a violet-y indigo color. And you might go for a quick swim. It was the tradition on Christmas Day at what was Faraday to go for a quick dip and then dash inside for a cold shower, which felt really warm compared to the sub-zero waters, and it left your fingers and toes tingling for the rest of the day. Moving on to climate. Climate is the sum of the weather over a longer period of time. And I showed you before that the averages give you these sort of -30 at somewhere like Halley during the winter. But that data is collected by either manual or automatic stations scattered over Antarctica. This is one of the ones that we had at Halley, which is measuring things like temperature, pressure, wind speed, and direction. And in this particular case, also the snow height, because at Halley, the snow surface steadily builds up, and you need to be able to dig out your station before it gets completely buried. And data from places like this all over the world are used to produce monthly averages of what the climate is doing. And this is the most recent hot off the press one, showing the global picture and how far the temperature is differing from the long-term norm. And you can see that the vast majority of the Earth's surface is warmer than might be expected on the historical basis, apart from in the Pacific, where there's an El Nino or La Nina events taking place. So there's cold upwelling waters that are moving out across the Pacific. But climate is very much influenced by regions as well as the globe. And it's quite important to look at climate change on a regional basis as well as a global basis. And it's definitely not something that happens uniformly. So for the area of the Antarctic Peninsula stretching to the Falklands and South Georgia, the pattern of change was a slight cooling until the 1920s, followed by a warming, and then a last couple of decades, pretty much a standstill. The consequences of that warming, though, are quite clear. Many of the locations that I visited, the ice has clearly retreated in the time that I've been visiting the continent. And when we look down from the air, we can see that there are more and more meltwater pools in the summer on the surface of glaciers, and that just weakens either the glacier or the ice shelf and makes it more vulnerable to distortion. And studies show that roughly 87% of the glaciers on the western side of the Antarctic Peninsula are in retreat, and a few are advancing. The fact that they're advancing doesn't necessarily mean that they're in good health. It might just mean that there is more snow loading at the starting point of the glacier, or better lubrication of the glacier bed so that it can actually flow faster out to sea. On the east side, some of the consequences of that meltwater forming on the surface are quite dramatic, and the fringing ice shelf on the eastern side has steadily been breaking up, often in sudden catastrophic events. And this was one particular one in the early years of this century, where an arch, which was effectively damming the ice behind it, broke, and then that allowed all the ice to flow out to sea. So as scientists, we need to look at what the causes of climate change might be, both on a regional and a global scale. And on a regional scale, one thing that can change the climate is a slow meandering of the ocean currents that transport water from the equator towards the poles. and decadal scale meandering of those currents will influence the regional climate. Volcanoes can influence the climate. This was a small Antarctic one that erupted in the 1960s and caused us to abandon one of the stations on the peninsula because it was completely buried by the debris from the eruption. But a bigger one was Mount Pinatubo and Sarah Hudson, which erupted in 1991. And they very clearly affected both the climate and the ozone layer itself, because it put a lot of debris high into the Earth's stratosphere. And of course, as the very recent eruption earlier this year of the Tonga volcano, which I think is the loudest bang of the last several hundred years, perhaps, since Krakatoa itself exploded. And it's very clear that this put a large amount of water vapor up into the stratosphere. That will have consequences. It's not entirely clear whether that has affected this year's Antarctic ozone hole. Certainly, as I'll show in a bit, it's quite a large ozone hole. And equally, I'll be looking forward to seeing what the stratospheric temperatures do when the end of year figures are published. And then there is the sun itself. We know that the sun is a variable star. There are sunspots on its surface. And as the sun rotates, those sunspots come into view and disappear. The number on the surface changes, both on a short time scale and a longer time scale. And as you know, surrounding those dark sunspots are brighter faculae, so that when the sun is more active, it's putting out a little bit more energy, so potentially warming the Earth. And on longer time scales, there is the periodic 11-year, or it's approximately 11-year solar cycle between a minimum and a maximum, and then longer period cycles of 100 or more years, where you change from a rough minimum, as in the 1900s, to a higher maximum. And some climate skeptics pointed that, well, look, between 1900 and 1960, the maximum sunspot number was going up, the temperature of the Earth was going up. That proves it's the sunspots. But a coincidental relationship is not necessarily a causal one. And the skeptics couldn't explain what happened after the 1960s when the sunspot numbers started to go down, but the temperature still kept going up. And having exhausted all those possibilities, that just leaves what we're doing to the atmosphere through agriculture, industry, and transport, which are leading to ever rising amounts of carbon dioxide in the atmosphere. Now, we've got in situ measurements over the last 60 or 70 years, and we can go a bit further back if we look at bottles of wine and things like that, because we know when they were bottled, and we can look at the little bit of air that's in them. But to go further back in time, we can go to the Antarctic and look at the layers of ice. This is a big tabular iceberg, and you can see layers in it. Those are akin to tree rings, and if you count the layers, you can work out when the snow fell. So our ice chemists drill down into the ice with a mechanical drill, recover a core, and analyze the water and the oxygen bubbles, or the atmospheric bubbles that are trapped in the ice. And that shows, if we look over the last ice age, that there was quite a rapid warming at the end of the previous interglacial period, a slow cooling to the maximum of the last ice age. And everybody else who's online can see, but those who are in the lecture theatre can't. So while the system is started up again, and I'm doing quite well for time because I'm halfway through my slides, so that's good. Fingers crossed. Yep, we're back. So hitting a minimum at the maximum of the last ice age, a rapid recovery, and then a period of stability when humans largely evolved to their present state. And then since the Industrial Revolution, a really dramatic rise in carbon dioxide. And there's two things in particular I want you to notice about this. One is where we are now, and the October value is 415 parts per million in the atmosphere. And that's about as much above a normal interglacial period as a glacial period is below. The glacial period is about 8 degrees or more colder than it is at present. So it might be worth arguing that the steady state solution for the amount of carbon dioxide we've got in the atmosphere now is going to be considering more than 1.5 degrees warming. We only talk about 1.5 degrees by the end of this century. That isn't the steady state solution. The other thing is the time scale that we're making the changes on. We are doing in 30 years what nature took 1,000 years to do as we came out of the last ice age. And that means living systems are going to find it very difficult to respond on that time scale. Do these changes matter? Well, certainly for us in East Anglia, they do, because an awful lot of East Anglia is at or below sea level. And if the tide and weather systems get it exactly wrong, you can amplify a 30 centimeter rise in sea level to a meter or more. We're now thinking that by the end of this century, it could be a meter rise in sea level. And if we get one of those systems that get it exactly wrong, the flood defenses will be overwhelmed. So it is of immediate concern to people living in the UK, because East Anglia is our most productive arable area. Heading back to the Antarctic, one of the first signs that you're getting close to the continent is in the sky. And you can see in the background, there's a bright area of sky. The cloud is exactly the same everywhere, but underneath the cloud there is ice. And the ice has an albedo, a reflectivity of about 80 to 90%. So the light is being reflected up to the clouds and then back down again. Elsewhere, it's open ocean, which has an albedo of perhaps 30%. And the ancient whaling captains would use this effect when they were stuck in leads of the ice, because they could look up at the sky on a cloudy day and see the safe route out mapped for them. And sailing through pack ice can be quite tricky, particularly if it's under any pressure. And I've certainly been on board our ships more than once where there's been nothing left to do but just wait until the pressure eases. But then you get through the pack ice to the shelf ice near the continent. You transfer to snowcat for the journey to the station, and then you're at our Halley station. The early Halley stations were built underground. Well, they weren't built underground. They were built on the surface, but the designers forgot that when the wind blows, it moves snow around. And if it encounters an obstruction, it tries to smooth out the obstruction. So anything on the surface quickly gets buried quite deep underground. So then we went to surface stations that were fixed on steel legs, and then finally to a station that can be towed to a new location on skis. And the Halley station is named after Edmund Halley, the famous astronomer, who's perhaps best known for his comet. And I was lucky enough on one of my trips in 1986 to see the comet from the Antarctic Peninsula. So I was the first person ever to see the comet from Antarctica, which is quite a good little tick. And in this, you can see the shadow of the mountains of the Antarctic Peninsula at the bottom there, and the comet rose tail first, a bit like a searchlight beam, because the atmosphere really is clear right the way down to the horizon. But Halley wasn't only interested in comets. He was interested in the Earth's magnetic field, in meteorology, in phenomena of the upper atmosphere like aurora, in the Earth's tides. And they were all things that were going to be studied at a new station that was being built in the Antarctic for the International Geophysical Year of 1957-58. It happened to be the tercentenary of Halley's birth. He was also a secretary of the Royal Society. The Royal Society had funded the expedition, so it all tied together quite nicely. The present station is certainly one of the major meteorological stations, and that white hut in the mid-ground is our balloon launching facility, and I'll show you a picture of launching a balloon in a minute. But inside, there's pretty much everything you might expect for a recreational time. So you can play table football, pool, and in the background is the station bar. In the winter, this is about as bright as it gets. You do get a bit of a glow in the sky at midday, but that's all. But there are other lights in the sky. Now, at the top of this, you can see a few streaks and things. That is a low-level auroral display. We quite often get that sort of thing in this country, but a light like that, you just think it's the next village street lights shining away. But at Halley, you can see the thing in all its glory. So here's a few quiet arcs meandering across the sky, and then display can become more active and become right overhead. And I've been fortunate enough to see one of those displays from the observatories where the aurora was right overhead and you could see rays diverging from the zenith. Sometimes the aurora can take strange shapes, and with a good imagination, you could interpret this as a ghost or a dragon flying through the sky. And that may be where some of the Norse mythology comes from. They would have seen the aurora in their night sky, and perhaps they interpreted it as living creatures that were fighting battles and dragons and other sorts of monsters. But today we know that it's caused by charged particles ionizing the Earth's atmosphere. And at Halley, there's a big radar array that's used to study the three-dimensional motion of the aurora. From space, we can see that when you talk about the auroral oval, it really is an oval. And Halley Station is interesting in that it is quite different geographic and geomagnetic latitudes. And that enables us to disentangle some of the effects that are due to geomagnetism from those that are due to geography. And I think we had a talk last year from Richard Horn, who explained some of the research on the aurora and how that it's the outbursts from the sun that compress our magnetic field, give extra energy to charged particles that have been stored in that magnetic field, and that they precipitate as the aurora above the two poles. Other exciting phenomena of the Antarctic daytime atmosphere are halos, and sometimes these can be really spectacular. Here we've got at the top a circumzenithal rainbow-like arc, but the colors are in the wrong order for a rainbow. So that tells you immediately that it's not caused by water droplets with light being refracted inside the droplet, but it's caused by reflection internally in ice crystals. Surrounding the sun on either side, there are two parhelia or sundogs, and there's actually a band of light running 360 degrees around the horizon. And I was lucky enough to see one of those at Halley Station, where there were also patches of light at 90 degrees to the sun, and they are called Hevelius's parhelia, after the Danish astronomer Hevelius, who observed them from, I think, Danzig. Associated with a halo display like that is a phenomenon called diamond dust, where little tiny crystals of ice condense directly from water vapor in the atmosphere and fall out of the sky. And as they catch the sunlight, they glisten and gleam like millions of diamonds falling out of the sky. Near Halley, there's a colony of emperor penguins, and I'm sure you've seen these on David Attenborough's documentaries. They're really quite amazing. They breed on the fast ice, the ice that's anchored to the shelf ice of Antarctica. The eggs are laid during the polar winter, and it's the male penguin that has to do the initial hard work of incubating the egg. The chick hatches and is looked after by both parents then. And by the time I get to Antarctica, they're in this sort of stage where they're being looked after by one or two adults in a little creche to make sure they misbehave. Now, what you don't get on the documentaries is the smell. A penguin colony absolutely stinks. And if you're working with penguins, that stench gets all onto your clothing. So when you get back to the base, people know exactly what you've been up to. But all too soon, the penguins are fully fledged, and then it's out to sea to fend for themselves. So that takes me on to the Antarctic ozone hole. And the first question, of course, is what is ozone? Well, we breathe oxygen in the air. The oxygen that we breathe has 2 atoms in the molecule, whereas ozone has 3. And ozone is normally created in our atmosphere by the action of sunlight on oxygen at high altitudes above 40 kilometers over the tropics. And ozone was discovered by a Swiss-German chemist by accident. He was passing an electric current through water, expecting to make hydrogen and oxygen, and he noticed a funny smell. And he followed up that funny smell and found that he'd made ozone. It so happens that the funny smell is exactly the same as given out by rotting seaweed. So when people say, oh, go to the seaside and you'll get a good dose of ozone, no, you'll just find that there's rotting seaweed there. Another step in the discovery was from the astronomers. When they took spectra of stars, there was a cutoff in the ultraviolet at about 280 nanometers. Now, the theory of stellar emissions said that they must be emitting in the ultraviolet, and it was therefore postulated that there must be something in the Earth's atmosphere that was blocking out that UV light, and it transpired that it really was due to ozone in the atmosphere. But the next step really wasn't an accident, but something deliberate. A professor of physics at Oxford University designed in the 1920s and 30s an instrument that is still one of the world standards for measuring ozone. This is the Dobson ozone spectrophotometer. And it was Dobson who first sent one of these instruments to the first Halley station so that they could measure ozone from Antarctica for the first time. And I've been using one of these for many years. First of all, in a hut on the surface, which had little ski runners on it so it could stay above. And then in the new Halley station, where it was a much more comfortable environment. And what the instrument does is it looks at ultraviolet light from the sun coming through the atmosphere to the surface. The really shortest wavelengths of UV are completely blocked by the atmosphere. But if you're an astronaut in space, you do have to worry about them. And that's why when you see pictures of the Apollo astronauts walking on the surface of the moon or doing spacewalks from the space station, you can't see their faces. And that's because they have a gold visor that is designed to block out all the UV light. Light of somewhat longer UV wavelengths partially comes through to the surface, and the light of the longest UV wavelengths comes through pretty much unscathed. So by measuring the ratio of UV1 to UV2, knowing what the ozone absorption coefficients are and what the elevation of the sun is, you can calculate how much ozone must have been present in order to give you your observed ratio. And about the time that I joined the survey, there'd been a lot of concern that exhaust gases from Concorde or CFCs in spray cans might destroy the ozone layer. And as this is the chemistry lecture theatre, I put on a bit of chemistry. So this shows the process of creation of ozone high in the atmosphere, which needs really short wavelength UV, but also longer wavelength light can destroy ozone by breaking apart the molecules. And in the normal state of affairs, there's a balance between creation and destruction. But the theory of the early 70s was that if you put chlorine into the atmosphere, that would allow photocatalytic reactions to take place, which would end up converting the ozone back to oxygen. And those reactions could be interfered with if there was nitrogen dioxide in the atmosphere or if there's water vapor in the atmosphere. It turns out that this mechanism that was postulated here wasn't the correct one, and that was because the theoreticians had forgotten one key element, which I'll get to in a minute. So one of the things that we quite regularly do, or certainly used to do even more regularly, was hold open days at the survey headquarters here in Cambridge, where we'd show the latest exciting science to the public. And I thought, well, I'm working on this year's ozone data. My boss analysed 20 years previously. I'll graph them up. They'll be the same. And people don't need to worry about using spray cans. But it didn't quite turn out like that. And Joe Farman on the left, Brian Gardner and myself eventually put together a paper that appeared in Nature, which linked decreasing ozone amounts over Antarctica with increasing amounts of CFC. And Nature let us get away with plotting this graph where we deliberately reversed one of the scales so that at a glance you'd see that there's a relationship between CFC and ozone, but that is a circumstantial bit of evidence rather than necessarily causation. It turned out it was causative. Since then, values reached a minimum in the early 1990s, and since then there's been a slow recovery, but it's going to be at least another 50 or so years before we're back to the original levels. So the question arises, what is different about Antarctica? And the answer is that during that polar winter, the ozone layer can get very cold, can reach temperatures below -78 Celsius. And under those conditions, clouds form in situ in the ozone layer. And these clouds are called nacreous clouds or mother of pearl clouds, or rather more boringly, stratospheric clouds. And they are really pretty when you get to see them. And it's on the surface of those clouds that chemical reactions take place that converts the chlorine from the CFCs into chlorine monoxide, lock up the nitrogen oxides as nitric acid trihydrate, and allow, when the sun comes back, very efficient photocatalytic cycles with the chlorine monoxide dimer. And we can see this year's ozone hole forming. The white at the center, it's still dark, we can't do the measurements, but as the sun comes back, we see the forming ozone hole covers virtually the entire continent. Occasionally it can move north and clip the tip of South America and the Falklands, but in late November, early December, it begins to break up, and eventually by the new year, it's filled in again, and then the cycle restarts. You can also see that surrounding Antarctica, ozone values are rather higher, and that's because surrounding Antarctica during the winter, you get something called the polar vortex forming, which is a little bit like water going down the plug hole in a bath. It spins, and that acts as a barrier to ozone-rich air from further north penetrating into Antarctica. when the ozone hole is around, you can get burnt in as little as 5 minutes unless you take precautions. So we have factor 50 sunblock on, and this guy has made an aluminium shield to protect his nose. Now today, if you scrap a fridge, the CFCs that might have been in it have to be recovered. And all the world's governments have signed the Montreal Protocol. And that treaty is really working. The amount of CFC or other ozone destroying substances in the atmosphere is definitely declining. However, around about 5 years or so ago, it was found that one of the CFCs wasn't declining as rapidly as theory said it should. It was still declining, but not quite so rapidly. And it turned out that there was manufacture of CFC 11 in China. That is used for blowing foam insulation for building. Once the Chinese national government were made aware of it, the manufacture was very quickly stopped, and things are now on track again to where they should be. And it does underline one of the really important points, that unless you've got global monitoring of many of these trace gas species, you won't find when there are problems. One question that people ask is, well, why is there an Antarctic ozone hole if most of the CFCs are made in the Northern Hemisphere? And it's all to do with that temperature. The Arctic is an open ocean surrounded by mountainous continents, and that gives us the jet streams that wriggle around quite a lot more than they do in the Antarctic, which is a mountainous continent surrounded by an open ocean. And that greater meandering gives more mixing. So on average, the Arctic ozone layer is about 10 degrees warmer than that of Antarctica. And so those clouds are much rarer. However, on occasion, it does get cold enough for them to form. So for example, in 2016, there was substantial ozone depletion over the UK. And there have been a couple of occasions when I've been lucky enough to see those stratospheric clouds here in Cambridge. This picture I think I took over Parker's Piece, and you can see that there's some dark clouds, which are clouds near the surface, but the other clouds are still a little bit illuminated by the sun, and they would be at altitudes between about 14 and 20 kilometers. When we look at the upper atmosphere, there has been a slow cooling. Now, people think that global warming affects the entire atmosphere, but actually it's a bit like having a blanket over your bed. Inside the blanket, you're nice and toasty warm, but outside the blanket, it's a bit colder because your body heat isn't escaping to warm the room so much. And the same thing happens in the atmosphere. So we do get some cooling in the stratosphere. But there hasn't been any marked cooling over the last 20 years or so. Is this just a pause? And we'll see it plummeting. We can see the effect of some of the really big volcanoes. So Mount Agung material is put into the stratosphere, and that material can absorb some solar energy, and therefore it warms the stratosphere. So a question for me is, in 2022, will the annual average be warmer than it has been over the past decade or not? Certainly the lack of ozone has had a very big effect in Antarctica. And this shows the temperature difference at the base of the ozone layer. And you can see that there really has been a dramatic cooling since we started measurements. And that is because ozone itself is a greenhouse gas. So where you've got less ozone, there's less absorption of solar radiation at that level. But overall, it's a very complex system. There are many interactions between climate and the ozone hole and climate. There are also effects depending on what we put into the atmosphere. There are effects of the volcanoes. There's the effects of surface albedo. And in the Arctic, the more ice we melt, the darker the surface becomes, the more energy can be absorbed, the less ice there is. So we get quite a positive feedback. So that's the end of my formal talk about Antarctica and would be the position that the British Antarctic Survey takes. As with one of our previous lecturers this time, I'm now going to give you a personal viewpoint just for the remaining few minutes. So the ozone hole and climate change are not the only crises that affect us. There is the biodiversity crisis, where the sheer number of living creatures is in decline. We also have problems like soil degradation, plastics in the ocean, water pollution, air pollution, you name it, we are spoiling our environment. And studies by the WWF suggest that we are using the planetary resources here in the West at a rate that requires us to have over 3 planets. That ought to be blindingly, obviously, not sustainable, but our political and economic leaders still want to go on burning up ever more resources to fuel their pyramidal economy, which insists on exponential growth with more rich people at the top and fewer and ever more poorer people at the bottom. What we really need to do is look at the population of this planet and try and reduce it, particularly, I think, us in the West, because we consume more than most others. When I've previously given this talk, I've said what we need is a good plague. Well, we've had a good plague, but human ingenuity has managed to circumvent the effects of the medieval plagues, where the Grim Reaper took a dance of death with all. The rich and the poor, it made no difference. And the population of Europe was reduced by about 1/3. Another possibility is an astronomical one. We are monitoring most of the big things that come our way, but something coming out from the direction of the sun, we would definitely miss. And that could put an end to us, like it put an end to the dinosaurs. But rather better is education. Education of politicians and economists here in the West to show them what their models are doing, but also in the developing world, and particularly the female part of the population in the developing world, to give them more a say in their future lives, because at the moment they do not have very much of a say. So it's really important, that aspect of education, to make sure that people can decide for themselves what they do in the future. And if we don't heed the lessons, then Easter Island gives a sort of simulacrum of what might happen to us if you use up all your resources. One version of this story says that the islanders at Easter Island use up all their resources and died out, leaving only those lonely statues looking out to sea. Another version, of course, says it was us bringing them diseases that finished them all off. But nevertheless, this image shows that there is hope for the planet, if not for us, because the grass is still green and there are still flowers and there are still other living things on the surface. So I think although we're having a very good go at destroying much of our environment, we will never manage to destroy it completely. And that brings me to an end. Thank you for listening.
So now we move on to the Q&A session. If anyone has any questions, you can raise your hand, and anyone in the room may have any question, you can put it in the chat.
Yes.
It's really great talk. I've always wondered the pictures of the auroras. I've never seen one myself, But when people take astrophotography of the Milky Way, it's always much better than in real life because they just use really high exposure. To what extent is this also the case with auroras?
I think it depends on how bright the aurora is, how spectacular it seems. So the last aurora that I actually saw, I was cycling back from the Antarctic Survey along the Coton footpath by the Cavendish, and I looked across to my left, and I thought, there's something odd. The cloud's the wrong colour. Clouds normally, if they're illuminated by street lamps, are that sort of orangey colour. This wasn't orange. And there was a quite faint, not particularly spectacular auroral display, which I managed to grab a picture of from the observatory. But the really spectacular displays, pretty much what you see on the film is what you get with the naked eye. So I think the best one that I saw, well, there's two that I've seen. One was from outside Cambridge and one from the observatory lawn. And I think possibly the one from outside Cambridge was the best because there were reds, yellows, greens, a corona overhead with rays stretching to the horizon, moving all the time. And I just sat and watched because it was so stunning just seeing it. The one at the observatory, some of the PhD students wandered past. I said, stop, look, have a look at the aurora. And they just carried on. And part of that is because it takes a while for the human eye to dark adapt. And if you're not dark adapted, you won't see the same range of colour. And certainly some of the people down in the Antarctic, I would sometimes, when I was at Rotherham, go out and do a bit of meteor watching or something like that. And I would see these faint lights on the horizon, which I knew was the aurora. And on one occasion I went in to the bar and said, oh, I've just seen a bit of aurora. And some of the guys there said, I've been here 2 years and I've not seen it. And that was because my eyes were dark adapted and they'd never gone out. So they went out and had to look at it. So different colours, but it's a really stunning phenomenon when it's active. And as we're building up to a sunspot maximum, there's a chance that we might get another one. So it's worth watching for the auroral alerts. But I think 99% of them are false alerts, at least here in Cambridge.